This is the comparator circuit using the op amp. As you can see, when I change the potentiometer location, the voltage output from the op amp changes, and you can see right there's one particular location where the LED goes from non-conducting to conducting. The reason why it's more of a digital change rather than an analog one is because the LED has a required minimum forwards voltage for it to conduct, and as soon as the op amp reaches that threshold, it will immediately conduct, turning the light on. Here's the op amp circuit of a unity gain amplifier. The potentiometer changes the input voltage, which causes a change in the processing oscilloscope, as you'll see later.
Here we can see the response of the unity gain amplifying circuit of the op amp. As you can see, it doesn't provide the proper response when the input voltage is below 2 volts. The reason for that is on the data sheet, it doesn't provide a response under 2 volts. The response is from 2 to about 11.5 volts. Because the VCC for the op amp is only 5 volts, the response for the op amp in its current configuration goes from 2 to 5 volts, as we see here in this circuit. Here's the schematic of the non-inverting amplifier circuit. We start out with the assumption V plus and V minus are the same, are equal to each other. The current into these nodes is both 0, and that the op amp can provide infinite voltage or infinite power to keep this V minus equal to V plus. Using those equations, we can set up a little ratio right here for the voltage at the voltage divider, which just so happens to be V minus. And since we said that V minus equals V plus, we plug that in. What we get is this ratio right here. When we solve that for V out, we get this relationship. After simplifying, we end up with this. Then, to find out what our gain is, cancel out whatever cancels out, and we get our gain, which is right here. For the integrating amplifier circuit, I will use KVL through this section of the circuit to find out what V out is in relation to V in. What we find is we add the voltage from V in, and then we have the voltage drop across the resistor, I times R, and the voltage drop across the capacitor, which has this integral in it. And that's going to be important later. When we sum those, we get V out. Simple as that. We also have another relationship that's due to the fact that V minus and V plus are equivalent. V in plus, our I times R, the voltage drop across this, is 2.5 volts. Because 2.5 volts is what's being fed into V in plus. When we solve this out, we can find what I is, and then that I can then be plugged back into our equation that we found earlier. When we do that, and we end up with the ratio that is right here.
Here is the 10x inverting amplifier circuit using the op amp.
Here is the inverting amplifying circuit. We can see that the white line represents the input and the blue line represents the output. This is a 10x amplifier, which means if the voltage deviation between V plus and our V input with a 100 millivolt difference, our output is just about 1 volt. This sort of amplification would allow us to amplify small changes in voltages, allowing us to read it more precisely.
Here is the integrating inverting amplifying circuit.
Here we can see the integrating inverting amplifier using the op amp. What you can see is the white line represents the input voltage, and the blue line represents the output voltage. When we transition from being at the yellow line to being above the yellow line, the blue line goes down. And that's it integrating its way to being negative until it hits its limit at just under 2 volts. And that limit of under 2 volts is set out by the datasheet. Next, when we go below the yellow line, the blue line integrates its way up to the top, which is the maximum voltage of just about 4.5 volts, as provided by the power supply of the Arduino.
I hope you enjoyed and learned something.